Let's look at OpenStax College Physics Chapter 22, Problem 51. The force per meter between the two wires of a jumper cable being used to start a stalled car is 0.225 newtons per meter. What is the current in the wires given that they are separated by 2 centimeters? B. Is the force attractive or repulsive? So let's write down our knowns and unknowns. We know that the force per meter, so that's the force per length, is 0.225 Newton per meter. And we know that they're separated by a distance of 2 centimeters. And we're looking for the current in the wires and whether the force is attractive or repulsive. So I'll just say direction of the force. All right, let's draw the diagram. So here we have one of the cables. Here is the other cable. So first we have to figure out the direction of the currents. So remember that you connect one end of a jumper cable to the positive of a good battery, the other end to the negative of a good battery, and then the other side is going to be connected to the positive of the bad battery and to the body of the car. So there is going to be a circuit formed here, which means that the current is going to go around either clockwise here or counterclockwise. So there are the batteries in between here. What that means is that the current in one of the wires will go in one direction and in the other wire in the opposite direction. So I'm just going to pick the random directions as being down for this wire and up for the other wire. So just to differentiate between them, I'm going to call this IA and this IB. And I know that the separation between the wires is D 2 centimeters. All right, so what is going on? We know that current IA will produce a magnetic field around it. So if we place our thumb in the direction of the current, we notice that the magnetic field will circle around like that, where it's going to be going in this direction. So this is the magnetic field due to current A. So at the location of wire B, the magnetic field will come out at us. So this is the magnetic field due to wire A. But now we end up having current B being in the external magnetic field due to current A. So now we can apply F equals ILB. I should write that here. So F that wire B experiences is the current in wire B times the length of the wire times the magnetic field that A produced. And now we're going to apply the right-hand rule, the first right-hand rule, by placing our fingers in the direction of the current, bending our fingers out in the direction of the magnetic field, and ending up with a force this way. So this is our F sub B. So if we look at this wire, we know that it also produces a magnetic field, and that magnetic field is going to be circling around the wire so that the magnetic field on this wire due to that wire is also out. So place your thumb in the direction of this current and your hand should circle around, and the magnetic field at this location will be out due to that current. So then this wire also experiences a force, and that's going to be, the direction is going to be given by the direction of this current times the magnetic field of the wire times the length of the wire, and when we do the right-hand rule for this wire, we'll end up with a force going to the left. So the force between these two wires will be repulsive. So let's first do the calculation. So I have force that wire B experiences is its current times the length times the magnetic field due to wire A. Conversely, FA is IALBB. So that will be I sub B L, magnetic field due to A is mu naught current A divided by 2 pi R. R is the distance from where the current is to the location we're looking for the magnetic field, and we call that distance D. So then this will be mu naught L. Now remember that the current is the same. We have a circuit where the current just circulates around the wires. So IA equals IB. I will just call it I and square it, divided by 2 pi D. So we're looking for the current. Current will be square root 2 pi D F over L divided by mu naught. So we plug in the numbers. 2 pi D is 0.02 meters. F over L is 0.225 newtons per meter divided by 4 pi times 10 to the negative 7 Tesla meters per amps. Take the square root of this and we get 150 amps. So we know that the current in the wires is 150 amps, and we figured out earlier that the force was repulsive. So these are the two answers to the problem.